Stage is yours.
Okay, yeah, thanks first of all. Okay, happy Thursday. Yeah, thanks for the opportunity to speak here. I would like to talk to you about the challenges of serving LLMs, right, like in real life. Okay. One more word, like to the previous speakers, or kind of connecting to the previous speakers. We work really hard at Nvidia to support as many GPUs as we can, right? Like, believe me that, right? It's a quite tough job to be honest. I'm not in the hardware department. I'm not working there. I'm not claiming any, fame for that. But I just saw that a lot of people work really hard to ship, right? Okay. That being said, yeah. Okay. GPT, right? Like transformers, generatively pre-trained transformers, the big hype, right? Like, I mean, not only the big hype. I mean, there's surely something in it. Okay, and it started, let's say it started with GPT, right? There was a lot of stuff before, I know that, right? Like there was LSTMs, there was BERT, whatsoever, Transformers 2017, right? Okay, but I think it really started to take off with the GPT family from OpenAI, right? GPTs are decoder-only architectures. I don't have, I have slides, but I think we don't have the time to go really fully in encoder, decoder, whatsoever architectures. But on the right side, you can see very schematically a transformer, right? Here you have one decoder block, that's the mask self-attention, and you have a feed-forward neural network. That is one block, and these blocks are basically repeated many times. You give tokens as the input, tokens are embedded, right? And on the output, actually, they are de-embedded and then sampled. That is the architecture. So if you look at the first GPTs, the architecture, you can write it in 60 lines of NumPy, right? It's crazily simple, right? But they work really well. I mean, we know that as of now, right? It seems to work. Not even, let's not talk about the chain of thoughts or whatever, but it seems to work. But do you know when people realized what they have to do to make it work? Anyone? They have to scale it up, right? Like, I mean, they started with 100 million weights, with 100 million parameters, and now we are roughly at, where are models now? 100? 405, Llama 405, and some of the real big models are in the trillion parameters league, right? So, and you can imagine if you have if you are in the range of 70 or 400 billion parameters, running inference of such a model is costly, right? Like it's a ton of compute that you have to do. Okay, here is a list of models. This list is in no way complete. It's in no way ranked by any priority or whatsoever. There are, of course, the OpenAI models. They're kind of closed. I mean, at least the newer ones. Anthropic is a very, very famous choice, right? Like the Sonnet 3.5. Then from our Google guys, the Gamma, the free ones, and the open ones, and the Gemini. Question, Gemma and Gemini, are they the same architecture? Would you know? Would you be able to tell? Okay. Then, of course, Meta with the very famous family of the Llamas, Mistral. Nvidia has a range of models, Nemotron and also the Minitrons. Qwen, Phi, Starcoder, Snowflake is in the game, IBM, everyone is in the game, right? Okay, and here on the right side, you see just for the Gamma 2, you see basically the settings of the parameters. These models come in different sizes, so typically you start in the 1 or 2 billion parameter league. These are relatively small models, easy to serve, but in accuracy they are of course worse. Typically then you go to something like 7, 8 billion parameters, and then you go to something like a couple of 10 billion parameters, right? And of course they're getting more and more hard to serve. And if you look at it, I mean, the 27 billion model is already using 46 layers of the transformer block, right? Like kind of a lot. And if you go to the large models, we are talking about roughly 100 layers, right? Also, the hidden dimension in each transformer block grows a lot. In the feed-forward part of the hidden dimension grows a lot, and actually there's a lot of weights hidden there, right? And of course, also the vocab sizes are really huge. Okay, so why are transformers? Why did they succeed the LSTM so much or so easily? Would you know that? Why? Yeah, that's the thing, right? You can put a sequence in and you can train on the whole, you put an input sequence in, you have an output sequence, and you can train the whole thing in parallel. Compute all the losses, everything in parallel, huge number of matrix multiplications, so works really well. Now, we have a really good model, right? They're really good, but now we run inference. And we have a huge model, and now we are actually a bit in the limbo, because the inference runs one token by one token, right? And you have to go the whole path through the model. You have to do it for every token again and again. Super costly. So transformers, super efficient at training, and somehow not that efficient at inference, right? Okay, and actually, if you look in detail, it's not fully just token by token. Usually you have here this yellow part where you have a prompt, right? You have a prompt, you know what's a prompt. And actually the prompts are not just what you type. Typically there's a, before your prompt is a set of instructions that is hidden and that still is used to prime the model, right? So the initial prompt is usually quite large. That's the yellow part, right? And after that yellow part, basically the model starts to generate an output. Okay, it outputs one token, right? And after that one token, we have to run the whole inference again, adding basically this one token to our sequence and using the sequence again as an input, running full inference again, 400 billion parameters, meaning whatever number of flops we have to do in the forward pass, right? Okay, and that's basically what I try to show here, that you have a sequence that goes in, you get a token 578 out. Now basically you append that token to the sequence and you run it again through your decoder model. Doable, very costly, right? Okay, so when we look at the speed of inference for LLMs, we look at several metrics, right? We look at the time to the first token, TTFT, and we look at the inter-token latency. So time to first token is mostly determined by the length of the prompt that you put in, right? Inter-token latency is basically when you really do it in the recursive, autoregressive way, right? When you generate token by token. And of course, the whole thing you would call latency, right? Like the whole time, beginning to end, you would tell the latency, right? Latency, what do you want with latency? Up or down? More or less? Less, of course. You don't want to wait for the token, for the response to show up, right? Then throughput is basically how many tokens you can get through your system in a given amount of time, in a second per GPU, right? Or per accelerator. What do you want with throughput? Up or down? Up, of course, right? But typically when throughput goes up, when we put our settings so throughput goes up, then latency also goes up, right? So we have a trade-off. We have the typical dilemma, right? Okay, what can we do to make throughput go up? Larger batch size, right? Larger batch size is cool, makes serving more complicated. For example, think about you have a range of users. You have like 50 users, but you have a batch size of 128. So yeah, what do you do with your batch? You can't fill it up, right? Actually, think about user traffic when you serve it. It's more complicated because you get this user traffic asynchronously, right? So you have to dynamically basically see how you fill up your batches, right? And what you do. Okay, very quickly, high level, not super precise GPU performance. GPUs, what are they? They're kind of supercomputers on a chip, right? They can do massive numbers of floating point computations in parallel, right? And basically, they can run tens or hundreds of thousands of threads in parallel if you instruct them right? They have tensor cores that are there to speed up matrix multiplication, so they offer even more flops, but Do you know what's the dilemma of the modern GPU? Your memory bandwidth is by far not high enough actually to feed in the data in, as fast as you can compute. So if you don't set up your kernels on the GPU right, you're mostly bandwidth bound, right? Like you cannot shuffle the data into the GPU and basically results out. I mean, your multiplications, you could do them faster if you would be able to magically get the data into the GPU. And again, think about it. Every inference with a 405 billion parameter model, you have to load all 405 billion parameters at some moment into the GPU, right? For every inference, every token, again and again, right? That's why basically we get, even with these modern and very powerful GPUs, we get only, let's say, a couple of hundred tokens per second out of them, right? When you write a GPU kernel, what you do is basically you try to manage memory, right? What you try to do is basically load data once and run many computations on that data before you write results back. This is called operator fusion, right? You can tile data in a way so you reload it not that often, or when you reload it, you try to make sure you have cache hits, not misses. So these are basically the kind of gimmicks that you do when writing a GPU kernel. In detail, it's much more, but that's roughly maybe a high-level overview, right? Okay, so what do people do to make the inference faster? And there's a whole kind of business model around these LLMs, right? Around LLM inference. So quantization, Aspen mentioned it before, right? Like if you quantize your model, if you quantize the weights down, the model can be served much faster. If you just remember what I said like one slide before, so if you quantize, you go from 32-bit to 16-bit. Why is it now so much faster? Yeah, it's half the amount of bytes you need to move, right? And we are going into this in a moment. Another approach is batching and caching, right? Like caching basically means you take the results that you computed before. Remember, an LLM works on a sequence of data. So you compute for the tokens that you already saw before. You don't want to compute the full forward path for these tokens. So the only thing that you need to store for these tokens is basically the keys and the values from the attention layers. And if you can store them, you can save yourself the full computation, right? What you also do is different techniques that are about improved batching and also chunking down basically the sequence lengths into more manageable sizes, right? Architectural optimizations. There's speculative decoding. That's when you use a smaller model to generate an output, actually several tokens of output, and then you use your larger model, which is typically more clever, more smart, more accurate. You use that larger model just to verify that the output of the smaller model is actually correct, right? Okay. There are other techniques where we can basically go down with the length of the attention span into the past. That's called sliding window attention. Or we use multi-query attention, where we do not have keys and values for every query, but we group them by, so we have 4 queries that share basically one key and value head, right? Okay. Another thing, and Aspen also mentioned it already before, that's parallelism, right? Parallelism, and something that also, of course, at Google, Google, everything is massively parallel, right? And you do the same thing on the GPU level, right? You are data parallel or you are model parallel. I'll go into this in a moment. And the other things that people developed in the past is, of course, or not in the past, in the recent past, is a lot of numerical kind of tricks and cleverness regarding CUDA kernels. That's what I mentioned before. When you write the code in a proper way, the kernel code, it can be much, much faster, right? Okay, data types and quantization, right? Let's say 10 years ago, you would train most of the stuff in float 32. It's a floating point number, single precision. that was good enough for most of the stuff, right? Like, and then actually someone came up with bfloat, right? 16. And do you know what the B stands for in the bfloat? Binary? Anyone knows it? It's actually Google Brain, right? Like Google Brain came up with their own floating point format, and if you can see it right here, the floating point format is very interesting. It keeps the same number of exponent bits as the 32, as the standard 32 floating point number, which means it keeps the same range, and that's of course very nice when you quantize down. Right? You don't need to care too much for range overflows. The thing, of course, it has way less bits in the fraction, so the precision of the numbers is lower, right? But the numbers still span the same range. Okay? So and that's definitely compared to float 16, which has only 5 bits of the exponent, right? And then also you see it didn't stop at bfloat 16. It went down to floating point 8, where are actually 2 different formats, right? How many different numbers how many distinct values can float 8 encode? How many at most? 256, right? That's it. I mean, this is not really a number format, that's a discrete list of numbers, right? And it didn't even stop there. We are going to FP4, right? FP4, half a byte, 16 distinct values. It's not a float. It's not really what we would consider a floating point format. It's really a collection of values centered around 0, right? With FP4, you get absolutely fantastic speed up. Of course, memory bandwidth is crazy. Even a 405 billion parameter model shrinks down to 200 gigs. Super nice, right? So yeah. The absolutely astonishing thing is that LLMs still work with 4-bit quantization, right? I don't say that this works easily. There are very, let's say, sophisticated techniques to shrink your model or retrain your model on 4 bits, but nevertheless it works. Actually, Microsoft came up with a 1-bit kind of model, LLM model, which still seems to work. Absolutely crazy, right? Okay, parallelism, super, super important, right? There are several types of parallelism. The easiest form is data parallelism. You take your batch, right? Like batch can be whatever, 64 sequences, right? And you simply split it by the number, you divide it by the number of GPUs. So you put the first 8 sequences on the first GPU and the next on, next 9 to 16 you put on the next GPU. Super easy, right? What is the, I mean, it's easy, right? Like, not a lot of sophistication is needed. What is the disadvantage of it when you do it? You have same latency. You get several times the throughput, right? Like you have n GPUs, you get n times the throughput, right? The thing is, if your model is 405 billion parameters, and let's assume you use FP8, so it's 400 gigs. Is there any GPU that has 400 gigs of memory, right? Not a single one, right? At least that not, yeah, okay. There are some very exotic ones, right? Like, but in generally super hard. So we are coming to model parallelism when you split the model either vertically or horizontally, right? Tensor parallelism, basically, I would say it's vertically, but I'm not totally sure. Basically, you split tensors into chunks. I mean, each tensor, a weight tensor of the model, is distributed over several GPUs, right? Nice, because, like now I can fit a very large model, I can distribute it to let's say 8 GPUs, right? And each GPU needs to load only, let's say, 50 gigabytes of the size, right? Has its advantages. There's also pipeline parallelism. Basically, when I split the model according to the layers, right? We just said before that an LLM has, let's say, up to 100 layers, blocks of, not layers, it's basically blocks, a transformer block. So, the first 5 go on this CPU. What is the problem with pipeline parallelism when you do it? your latency goes up, right? Because think about it, like the data needs to first, or you put your tokens in, but they first go to the first GPU, the results from the first GPU go to the second, and so on and so on. Latency definitely goes up. Communication between GPUs is definitely slower than within a single chip, right? Like within. Okay, another technology, and I think I talked about it, use speculative decoding. Speculative decoding meaning people realize that actually in a sentence, right, some words are absolutely determined to show up at the next position, right? There is no choice. So you don't need a very clever model to predict what is the next word. Why is it so? There's grammar, right? Like grammar sometimes dictates what's the next word, right? Like, or gives you very little choice. So, and the observation is basically that a much smaller model, let's say a 1 gigabyte model, a 1 billion parameter model can actually mostly do the same tokens as a much larger model. It basically mistakes only on the very difficult parts of that, of a sentence, right? Like, or of a thought, right? So the idea is basically use a much smaller model which you can evaluate much faster, generate 4 to 8 tokens in advance, and then run them in parallel through your larger model. And the larger model just checks if the larger model agrees with these 8 tokens, right? If it says, hey, they look fine, you go for it. And basically you did 8 tokens at the cost of 1 evaluation of the large model. Of course, in practice, it's not as easy. Often you have a reject, right? That the larger model says, okay, first 2 tokens were good, but then you started to go off in some strange direction, right? So in that case, then you have to basically backtrack and start again after the second token. Still, it gives a speed up. Actually, when you look at it on code, it works much better. Speculative coding works much better. It gives you more speed up because code apparently is more easy to predict. Does it make sense? There's less ambiguity than in natural language, okay? A drawback of the speculative decoding is basically that you need 2 models. You need to host 2 models. You need to make sure they have the same vocab and the like. There are approaches like Medusa and multi-token prediction where you actually try to use the same model for, basically as the draft model and as the full model. Okay, key value caching, I already talked about it. It's a standard technique to speed up LLM inference. I think there's no framework that would work without. Basically, you store for your sequence all the previous keys and values. You don't need to store queries. Queries are only relevant for the current token that you want to basically predict, right? But you need the keys. It's kind of a nearest neighbor lookup in your... Actually, transformers are just nearest neighbor lookup machines. How much time do I have? 2 minutes. Okay. The problem with the KV cache is the following. KV cache works super nice, but your problem is that it takes a lot of your memory on your GPU. And the memory scales linearly with the batch size, so this is usually one of the main limiting factor on a large batch size. Okay, you can skip this. Algorithmic or kind of numerical gimmicks, not gimmicks, sorry. Optimizations, flash attention. Who did hear about flash attention? Okay, a few, but not many. Actually, super cool stuff developed by tradeoff from Stanford, already in the 3rd kind of version or 3rd generation. And basically, there's someone that looked at the attention, how the attention works, how you do the dot product, and how you do the softmax, and basically slimmed it down massively, programmed in a way that the memory bandwidth is maximally utilized, or basically that it uses a lot of data locality to not get the data from the HBM. So super cool stuff, right? Like and uses like a lot of like esoteric CUDA voodoo to make stuff fast, right? Okay. Inference frameworks. I'm listing here a few frameworks. So the good thing is when you run inference, you don't write all of the stuff yourself. You use one of the inference frameworks. Let me start with a few. There's TRT LLM. I'm of course saying it because this is published by Nvidia. It's free. You can use that, right? Like We are relatively proud on it. It's developing a lot. So I mean, actually, with each new model generation, you have to update these frameworks, and it's actually a lot of work to keep this really, let's say, on the same state as the models that are released. Another super how to say it, popular framework is VLLM, open source, very good. We have to say it's really well written, and there's a lot of hype around this. DeepSpeed is, I think, something that people use. TGI, llama.cpp, very interesting. It has a CPP. I mean, it has a version that runs simply on CPU. You can run it on your MacBook. You can run some of the large models relatively easily on a MacBook with, if you have enough memory. Same for Ollama. Actually quite cool stuff. Of course, you can try to run inference simply with torch compile. That's also possible, right? Like relatively slow. Now comes, so the challenge is actually, there are all these different techniques, and all of these techniques have parameters, I mean settings, right? How much tensor parallelism do you use? How much pipeline parallelism, right? KV caching, how you do it. There are tons of kind of settings, right? Do you chunk it, right? So Nvidia came up with a solution that we call NIM. NIM are basically Docker containers that we have prepared. In these Docker containers, you have basically a set of libraries. I mean, you have all the dependencies there, starting from CUDA, starting from all the libraries. I mean, the libraries. Then we also put on these in these containers. We basically put in, as you can see, we put in actually the TRT LLM runtime. We also put in VLLM, right? We are quite happy about that. And then we put an executor, the fast API that also was mentioned already today. And actually we use an OpenAI kind of API to allow basically when you have this Docker running to interact with it. So just for convenience, right? Not only for convenience. We think it's a relatively good API, right? So you don't need to change the way you interact. These can be downloaded. The pricing is a different thing, but I think for evaluation, it's definitely possible to download this. There's also a preview thing where you can, you get your token and you can, work with the API. We are trying to have most of the modern models supported extremely quick. Often it's day 0, so on the same day when they are published, actually, like on GitHub or Hugging Face. So we would be happy if you give it a try. The models inside are, no, let me rephrase. We put in optimized configurations for maximum throughput or minimum latency, or for a balanced kind of scenario. We put them inside the container, so you don't need to check, you don't need to run in hyperparameter tuning or whatsoever, or benchmarking yourself here. Yeah, I think, that's what I have for you today.
Let's have the questions. 1 or 2 maybe.
Thank you, great talk. I can't still wrap my head around how those V-floats and even shorter ones work. How do you not lose the precision?
You lose precision. You lose precision, of course. But I mean, that goes now a bit we are getting a bit philosophical, right? Apparently, the encoding that the transformers use, they are in some sense sparse, or they distribute the information very much along the whole vector, right? You have a state vector that goes from the embedding through all the transformer blocks to the output, right? And my take is this encoding it's not sparse in the sense that there are zeros, but it's a redundant encoding, like an error correcting code, right? I think there's no one that fully understands that or knows that why this still works. It works even if you go down to this 1-bit type of precision. I think you lose a bit of accuracy, but it's totally crazy that it still works, right? I think this is something that still needs to be researched and investigated to understand that better. Now, of course, when you quantize, it's not that this works out of the box. You often need to apply certain techniques, quantization techniques, where you basically do certain mutations or corrections to your weights to make sure that the accuracy of the model doesn't really suffer. That's 2 or 3 talks to talk about quantization.
Thank you.
Generally felt like you could spend 2 or 3 talks on each of these subjects. Do we have any more?
Hi. So why do NIM containers are paid? Why do you need to pay for it? Is there any proprietary software apart from CUDA?
No, it is basically the service, right? And the payment model, I don't, honestly, I don't fully know it, because it's, I think, even on an enterprise level, so it's kind of often a deal there. It is an amazing amount of work to shell out these containers. Like it's not 10 people, it's like many dozen people to do that. Actually, like we have some guys basically that sit there day and night and try to make sure that we get the day 0 model, where you get the parameters, you get a checkpoint like 2 weeks before, and they sit basically like, I don't know, way too many hours there to make sure they run. The point is with every new model, like a new llama comes out or a new company enters the game, it is like this, that most inference frameworks do not work out of the box, right? Like they have to do some adaptations to support the models, because typically new models change something in the architecture, or they rely on some feature that wasn't implemented so far, right? Like, let's say someone comes out with the sliding window attention, and then you need to have basically kernels for that that need to be implemented, right?
We need to switch to the next speaker. So thank you, Christian.
Thank you.
Presentation.
Let me sit.